Oh my goodness. What to do? I think I've got the idea that at this point, because of so much has been wasted, I'm going to let the stream run, but I'm just going to delete the first half when it goes up on online, rather than start again, because I don't know what that's going to do to the whole interface. Well, that's a shame. But I'll do like a brief overview of everything, and then we'll just have to leave it there. So, yeah, what was discussed? Thank you for pointing it out. Really appreciate that. So, the collection of data, I was just looking over the exam paper makeup, essentially. And we're looking at planning, so having to plan a statistical investigation. We're looking at the types of data which were talked through, but not necessarily needed to go into the same amount of detail, I suppose. It's just nice to have made the notes at the long side. Let's use, do we have some sort of... Let's use a hand. So with qualitative data, this worded data, not numbers. So we're collecting things like words. We can only really do that in terms of frequency. With quantitative data, the other type is numbers. And they come in two different types. Discrete, which we usually call counting, and the other, which is continuous, which we usually say we're measuring those. Some examples of counting are the number of pages in a book, because even if you rip a book, like a page in half, it's still a page. A really important one, also really important to spell it properly, number, the number of people in a room, because, you know, even if people are taller or smaller, if they have limbs tragically cut off, these are still whole people and they count as one. And a really important example would be shoe size, because with shoe size, we only have certain numbers available, right? So size 1, size 2, and everything there is a half in the shoe size, it's still only a certain number. And it gets us to asking, what is the difference? Like, when does discrete become continuous? Now, there's a good argument in terms of populations being finite and infinite here. When you have to count something in its shoe size, you essentially have a number of different people with the same shoe size. 7 people will have a shoe size of 8. 2 people have a shoe size of 10. So you get this repetition. And you're still like counting. When you have too many different shoe sizes, let's say there was 1,000 different shoe sizes and everyone was different, there's a stronger argument to say that this is continuous, because we can no longer count it in the same way. And this is when discrete becomes continuous. And it's a moot point, a point that you have to decide upon. Our capacity as human beings is limited by technology, intellect, time, money, etc. And yeah, when you have too many different data points, let's look at it from the other point of view. For continuous, it's usually something you measure, so like time and speed and height, because you can measure those to any accuracy you want. And you're limited, I suppose, by your ability to measure them, but they are continuous. And as far as we know, time is continuous down to the smallest measure of difference, that we maybe one day we'll find that time is discrete, that it's, you know, one frame to the next rather than just smooth. And it's one of the difficult things, like technology, we can't really experience those sort of things. We have to rely on technology to do it. So with the world without technology, we really got a big distinction between these two. So when does continuous kind of look like discrete? Well, continuous, let's say we're measuring the height of people in a room. You might say that everyone has a different height. If you were really accurate, you would say everyone is a different height, even to a difference of a hair width. And our ability to say that people have a different height is dependent on our ability to bother measuring. If we both stand next to each other and say, yeah, we're roughly the same height, that's a little bit negligent in terms of accuracy, because if we if we rounded it, for example, a lot of people would probably become very similar in height. And if you're then counting people, like the number of people that are at a certain height, you're essentially going to be discrete in a way. It's going to be like shoe size. And so I mentioned at this point that we have something called a rounded continuous data, where we round it to the nearest whole so that it's nicer to work with. And maybe we just don't care about the accuracy. But if we do have rounded continuous, we could have it come from a continuous distribution of data, but then work with it in a discrete way. So that's when the continuous could become discrete. Yeah. Okay, so population and sampling. This was the diagram over here. So obviously, if we've got a sample, it's going to save us time because we're going to take less time to get it, less work to do. And if you're going to save time, you're going to save money. But you need to represent the population. It doesn't always do that. So here's the diagram over here. We have the reds to greens on the left-hand side. This is the population. This is all of them. And there are 10 reds and 5 greens, and that's approximately a 2-to-1 ratio. If we look at the sample at the top and the bottom, we can see down here, the bottom one is a randomly picked sample, and it's made up of 6 red and 2 green. And that's a 6-to-2 ratio, which simplifies to 3-to-1. Okay, it's not too bad. It's quite similar to the original 2-to-1, but you could argue it is not the best sample, but it could be worse. And if you look at the sample up here, they're all red. If you're talking about random samples, you're not in control. You're trying to take away your own bias and say, well, I didn't have any hand in this. But at the same time, if you're randomly doing it, it could pick all the red. And if you only had this sample to go with, you went and collected your data, and we know this is bad data now because we see the population, you might conclude that the entire population must be all red. And obviously that's not the best. And so you've got to be really careful about your sampling. Now, the smaller the sample, the more difference in variation you're going to get. The bigger the sample, the less variation you're going to get between, and the more towards the truth. And that's why when we're taking a sample, and this is a good thing to add, we need to make sure that we have at least 30. Now, this is a interesting amount because some would say that's not very much, but it's just the standard for this level. So we want at least 30 data points, and this is going to give us statistical significance. We all know the difference between something that's significant or not, because based on anecdote, like a simple sample that we have, we could go off and make conclusions about the population rather foolishly. And that would be anecdotal. The whole point of statistics and why we study it is because we want to eliminate that idea. We want to be a bit more sensible about the limitations of what our data is saying. So we look for situations and we gather the data that will give us more concrete conclusions. And there's at least 30. And then go all the way to the extreme and you have the population. Here's the population up here, the big one. And if you take that, well, it's accurate, but good luck because it's expensive. It also takes a lot of time. And actually, it might be impossible. There are situations where you're trying to take like the census, like everything. That if you might destroy the product in trying. So let's say you had a production line of chocolates if you wanted to test every single chocolate, like the whole population, you're not going to have a product. So it doesn't make any sense to do census. Could be unethical. So if you wanted to collect every single animal of a particular genome out in the wild, you're disturbing all of them. And that could ruin their survivality chances. And non-response rates are a thing, you know. It's very hard to get people to respond. They don't have access to the internet or telephones or even an address. It's mostly not possible to get a census. But we try, because the closer we get to a census, the more accurate we can be. And we know that there'll be less variation in the samples. For example, if we took a sample of the population of 15, we'd literally have all of them. And any conclusion that we drew would be perfect. Estimation. So how do we use sample data to estimate the population parameters? There's a number of sophisticated methods there. It's all about our sample and what we can tell about the population using that sample. So getting a good sample, getting good data is really important. Collecting data, there's a number of different ways of doing that for primary data. And I added in here cleaning the data, because when you collect it, you might make errors. You might make obvious things that if you put it into a program and say, plot it for me, it's not going to understand. It's not going to compute. Okay, so processing, representing, and analyzing. Once you have good data, we move on to that. We might have tabulations, very basics. So we're talking about frequencies. There's usually bar charts. We could do summary statistics. And these come under the guise of measures of central tendency, where these three, the mean, the median, and the mode, are all attempting to derive a single number to represent the center of the data point, the data, so that we can compare two different data sets. We can't really compare without that one measure. And then you've got spread, so dispersion and spread. This is where we talk about range, interquartile range, variance, standard deviation, as good measures of how far apart they are. We may instead not be talking about a comparison, but in fact, I want to write that there. So measures of central tendency tend to be comparative. So you're trying to compare two. And then another type might be looking at relationship. So with the scatter diagrams and correlation, you would be plotting a scatter diagram. And that line of best fit, oh dear. Let's lasso that down a wee bit. So you may have a scatter diagram. I think there's a really cool way to draw a diagram in here. If we're in the drawing phase, actually maybe, is it shapes? Yes, shapes, and here. This'll do. It's better than the old one. So in this, you may have two different variables, and you draw, what should we call it? Call it variable 1, variable 2, and you may have a scatter graph that looks like this. And you do have something called a line of best fit. And the line of best fit will go roughly through the middle, right? So what are we're talking 1, 2, 3, 4, 5. Let's do there and let's evaluate. Maybe we'll have the same crosses on top. 1, 2, 3, 4 on the top, and 1, 2, 3, 4 roughly. Okay, it's roughly the middle. And this is our line of best fit. And we have the distance away from all of these. So these crosses, these data points, are away from that middle line. And the amount that they're away is called the scatter. Like when someone scatters and runs away and spreads, that's scatter, that's the definition. That's why it's called a scatter diagram. And the closer that things are to this line, the stronger the correlation. Like a perfect correlation would be a straight line. But like it's hard if you don't put a measure on it. And this line is called the regression equation. It's like y equals mx plus c. It's a straight line. And you can tell how close all of those are as a strength, all of those crosses, with a measure called the PMCC. And that's part of this course as well. It's just here. So the PMCC gives you a number for the correlation, and the correlation is just how close together these crosses are. How do they follow that line? Are they close to that line? And essentially that's the relationship between the two variables. To do this type of analysis or relationship, you need to have bivariate data. Bivariate data is where you collect two pieces of information on each case, and that could be the height and the hand span for everyone in the class. That's what these variable 1 and variable 2 are, height and hand span. And, each dot, each cross on the scatter diagram represents one person measured by two variables. It's also important in this course to talk about independent variable. Okay, so the independent variable is the one that goes across the x-axis usually. And it's the variable that is moving independently. Some good examples of this would be time. Some you might argue weather. And that would be in contrast to the thing that these variables are affecting or explaining, right? So I could give a really good example with weather. And I'll talk about that in a second. So you've got the dependent variable, which is affected by the independent. Sometimes we call the independent variable the explanatory variable, because it's explaining what's happening. And the dependent variable, which is affected by the dependent, is sometimes called the response variable, because it's responding to the independent. And some of these that might be common but not strictly would be sales as a result of this, or growth, things like that. So I want to give an example of why this only goes one way. And the best example to use, once we clear a bit of space, is ice cream sales and weather. So we can say that as weather gets warmer, ice cream sales go up. That makes sense. But does it make sense backwards? Is it true that if we go out and buy a ton of ice cream, everybody, it will suddenly get warmer? And this is a really good example of why it doesn't make sense. So choosing what the independent variable is, or knowing what that is really important, because the relationship that you find with this scatter graph only goes one way in terms of predictions. we can't really go backwards. It's a bit invalid for our argument. And finally, time series. So we're talking about how things change over time. And this is very psychological usually, because it's down to the patterns of society and humans, and often something to do with sales and price. And it's guided by very random desires. And so you can look at patterns, because we often work in patterns as people, and it's affected by the weather, for example, or things that are going on, which are also cyclical. And over time, we see patterns. So we measure this one variable over time. So looking on the right here, we have a time series, which is price over time. And it going up and down, all over the place, right? And this red line represents the trend, the general upwards trend. And there's a really important lesson to be learned about this. If we worked in, so we've had this journey day by day, let's go over with a highlighter, and we're going down and then up, and then, oh my goodness, all the stocks are going down. Maybe we should sell before they're all gone. Oh, but wait, we're going up again. We're way higher than we've ever been. Maybe we're going to keep going up. Let's buy more. Oh, they're going down again. So if we live day to day, we're totally, we're dramatic. Yeah. Day to day drama is, very stressful. But what is this red line? This red line represents the moving average, which is a general upward trend, which is way more powerful. We calculate this line using something called moving averages. And in the world of finance, yes, for Edexcel. In the world of finance, we have, I'm not going to say it's for any particular exam board, actually. These are topics which are very useful, but yes, I was looking at the Edexcel specification. So, yeah, in the world of finance, with the moving averages that works really well are the 3, maybe the 9, but also the 200. So all of the banks look at a 200-point moving average. It's crazy. And this generally steadies the ship, because we're not going to look in the short term and get all panicky. We're going to look at the long term and say, what's going on? If we just invest and then chill out, over time, that money will go up. So moving averages, really important in the world. Further summary statistics include such things: Z-scores, standardized scores, and quality assurance. Standardized are really important because scales can be all over the place, but if we standardize them, they can be compared no matter what those scales are. Probability slips in here a little bit more than your GCSE average, kind of some of the stuff that you'd see in A-level, actually. A difference between experimental and theoretical probability. Provide examples here, for example. We've got experimental probability, and that's often taken as the truth. So if we go out and do an experiment in any hypothesis, like a hypothesis testing situation, we will run an experiment to find out the truth, because it's literally happening in the world. You can't argue with it. And then the theory, there's a difference here. The theoretical, which could be a number of distributions or just basic probability, is the idealized idea of what should happen. For example, if we roll a dice 240 times, how many 5s are you going to get? Well, you might think 40, because everyone should appear equal amount of times, right? A sixth. But really, when we start to do this experiment ourselves and add it up, all of our dreams get shattered when we start seeing certain numbers ahead of others, right? They don't count nicely. They don't go, you don't roll the dice and get a 1, then a 2, then a 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. What we end up getting is maybe 5 1s in a row, and then well, where's the balance? And we still haven't had a 6. We haven't had a 6 all the time. It's just random. And we're dealing with that chaos, right? So the theory is nice, but the real world, it's not. And the theory has to match the real world, right? So when we have these basic ideas of probability, they don't always work in all situations. We have the probability distributions that might model the real world better. And we have to recognize the type of situation that we've got going on. So if we're looking at a type of situation where there's a win or a loss, you've got two outcomes, and there's a fixed number of trials, then we're looking at binomial. Like, for example, flipping a coin 20 times and then measuring the number of heads. It's either heads or it's not heads. It's not heads or tails. It's heads or not heads. For a normal distribution, sad as it is, most cases in a population are average, which is not too bad. When you're looking at the height of people in a population, you can accept that because there's no real judgment on people's heights, not really. When it's IQ, there is. And so, yes, the average IQ, there is an average intelligence if you believe that IQ is a measure of intelligence. And we'd say most people are average. Let's carry on with a height example, though. You're going to need an average and how spread out it is. So you could have something which is quite close to the average. Most people are average, but you could also spread out as well. And that's how we identify what type of model might work best because of these characteristics of what we have in the data. So these are the kind of things as a rough guide of the basics that need to be in place for statistics. And having a look at some of the past paper questions, created some other questions just to give you a refresh if you've got to that point where you just want to go through some stuff and make sure you got it right. I also wanted to give you an idea of where this stuff is used in real life, because in the exam, you have real life situations all the time. So for the descriptive statistics, they're used in hospitals. So like patient data and like average length of stay, median recovery time, and common illnesses to improve patient care. In retail, we are using the sales data to determine average sales per day, median sales, and frequency sold over time. With finance, we've got the investment firms are using the interquartile range to understand distributions of returns. And in quality control, so we use IQR as well to measure variability in product dimensions, because the IQR is a really strong measure of the majority of the data and how spread out it is. And if something is less spread out, it's more reliable. So these are really good scenarios, and probably, anyone could come up in the exam. So here's some questions. We'll go through them now. What is the mean of the data set? Well, we're going to add them all up and divide it by how many there are. Now, you do get a calculator, so there's no harm in getting a good one, such as the one I have, which is the Casio FX991EX. It does a number of things that's useful, like, for example, calculating binomial probabilities. Okay, so it does the binomial distribution. It also does the normal distribution. It also calculates the PMCC and the formula of the regression line. So all of these things can be done in a whiz bang. And that can be useful to save time. It solves quadratics. It does a number of things. We won't go into it fully, but I think I've said enough, and I think that's really, if you can afford it. I did get mine for around £20. It was imported from India. So if we sum the data, and we call this data X, the formula that you might be used to seeing is the sum of X over N, which is however many there are. The sum of X is 70, and the amount of data we have is 6. So it becomes 11.6. Now, I would definitely argue that fractions are really nice, and I don't think you're going to get marked down there. So fractions are what we call exact numbers, and I would prefer them over anything. But it doesn't always show you the rough, size of it. 11.6, we can put that in the data set somewhere. It's around here. And we can double check that it's roughly in the middle, and it is. find the median of this data set. So the median, 1, 2, 3, 4, 5, 6, that's even. When it's even, we know it's going to be in between two numbers. There's a couple of ways of doing it. Let's do it the basic way, where we work in from the outside. And the median is going to be in between 7 and 9. So if we want to find the midpoint of any two numbers, call them A and B, that's going to be A plus B over 2. In our case, we've got 7 plus 9 over 2. So that's 16 over 2, which is 8. And you could have figured that out in your head. I know you could count on a number line. And you could say, oh, well, there's obviously 8s in the middle. But to be honest, when the numbers are not like 7 and 9, this is a really nice method to have. For example, if it's 181 and 277, and you need to find the middle of those two, add them up, divide them by 2. So you can see how it can be useful if the numbers are a bit more nasty. Okay, so there's one way of doing it. We're counting. I want to look at a more sophisticated way of doing it. When there's more numbers, this becomes actually really more important. So we know that the amount of numbers here are 6. If we do n plus 1 over 2, we're going to find the middle position. So that's 7 over 2, which is 3.5, the 3.5th position. And instead of counting in from the outside, which you can imagine is really laborious if you had loads of numbers, we can go straight to the third number and in the middle of the next one along. So let's use different color. Here's number 1, there's number 2, there's number 3, and 3.5 tells us we're going to go in between there, in between 3 and 4. So we arrive at the same number, but we're using this more advanced method of n plus 1 over 2. And that's going to be really crucial when it comes to finding a median from a frequency table. So we still come and conclude that the median equals 8. Identify the mode. It's really easy when there's only one. Here, the mode is the most common. And that's the frequency, isn't it? So the frequency here of 4 is bigger than any other. There's 2 of them. What about this one? You've got 2 3s and 2 9s. So this one is what we call bimodal. So that's 3 and 4. But you could, if you have any more, also have something called multimodal. So this covers everything that's more than 2. Okay? Bimodal, bi meaning 2. Yeah, cool. Range. Not the very good measure, to be honest, of dispersion is range. Range is where we take the largest and the smallest. That was the opposite order. And we find the difference between the two. So 55, take away 9, which is 46. So the range is 46. Shows how spread out it is. If we have a small range, a really good word to describe that is reliable. And the opposite is true if it's a large range. Okay, what is the lower quartile of quartile 1? So the lower quartile of this data set, how many do we have? We've got 1, 2, 3, 4, 5, 6, 7, 8 numbers, so it's a bit awkward. We can find the median first. The median is in between here. As we can see, we've got 8 numbers, it's going to be in between there. The median equals 13. Now, if the median is in between 12 and 14, 12 and 14 are still in play. So to the right of the median are 4 numbers, and to the left of the median are 4 numbers again. Quartile 1 is down at the bottom. So if we talk about what the quartiles are, we're splitting the data into 4. Quartile 1 is there, quartile 2 is there, quartile 3 is there. And you might wonder, well, why didn't you start at the beginning? Where's quartile 0 and where's quartile 4? Well, we only talk about that because it's the amount of data up to that point. So up to here is 25% of the data. If we go from the beginning to here, we've got 50% of the data. And if we go from the beginning to the third, we've got 75% of the data. And you've also got the middle section as well. Between quartile 1 and quartile 3, you have 50%. So each section represents 25%. And if they're squished up together, that means there's a lot of them in one place. So for example, you could have something like this. Then quartile 1 is really well spread out. Quartile 2 and 3 are close together. There's the same amount of people are in each of those sections. But clearly they're all squished up in the middle. So it gives you a little idea about the distribution. Okay. So there's 4 numbers on the left and there's 4 numbers on the right. Quartile 1 is down at the left-hand side. So of these numbers that are left, a quarter is a half of a half. So we've already done the median, which is a half. Let's do a half of the half. And so we find the midpoint of these 4 numbers, which is in between here. Now if I write them out again for you, I'll show you clearly. 5, 7, 8, 12. We're going to work our way in from the outside. So clearly the quartile 1 is in between those two. 7 plus 8 divided by 2, 7.5. Okay, and that's one way of doing it. I want to look at the more sophisticated way again, which if we were looking at the median, we would do n plus 1 over 2. But for quartile 1, we do over 4 because we want a quarter. So this is the location of the quartile 1. When it's 8, so that's 9 plus 1 over 4. That's 10 divided by 4, which is 2.5. It's the 2.5th location. And if we look on our, I can probably get rid of that. Okay, if we look on our data set, we've got 1, 2, and it's in between 2 and 3. So it's the same as doing a half and a half. You can see that if we had loads of data, this would be so much quicker. So doing the n plus 1 over 4 thing, pretty good. Upper quartile. So we've got new numbers here. How many have we got? We've got 1, 2, 3, 4, 5, 6, 7, 8 again. So we know that the median is in between here, and we're looking for the upper quartile. So we take the 4 remaining on the right, and we go to the middle. So we can see it's in between 12 and 15. So we do 12 plus 15 divided by 2, and that's 27, divided by 2, which is 13.5. That's quartile 3. Now with this, we're going to do it a bit more sophisticated. It's a bit harder when it's the upper quartile, but we can still do it. With the median, quick recap. With the median, it was n plus 1 over 2, because that was the middle. With the quartile 1, it was n plus 1 over 4, because we want the first quarter of the data. But if we want the third quarter, we have to multiply this by 3. So if I write it a bit clearer, it's going to be 3 times the n plus 1 over 4. Because this represents the 3/4 point. You could write it like this, 3/4 n plus 1. If you'd like to see it that way, it makes sense, doesn't it? It's n plus 1, and you want the 3/4 point. And if we put that in, we've got, what, 8 points plus 1 is just 9 times 3 is 27. And then we've got 27 divided by 4, which is going to give us the 6.75. And I always write like a location, because this is not the quartile 1. A common error here is to write that this is quartile 1, but it's not. It's the location. And so 6.75, let's count up in our data set. So we've got 1, 2, 3, 4, 5, 6. So it's in between 12 and 15, like we knew it was. But what's the 0.75? Does that confuse us? Guess what? It's still the middle. So even if it's 0.75 or 0.3 or 0.6 or 0.5, you still go to the middle of those two numbers. So 12 plus 15 over 2, 13.5. Good job. And then finally, we want to calculate the interquartile range for a data set. This is going to be putting all of that together. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 data sets this time. So n equals 9. I'm going to do it with the formula. So we'll first of all find n plus 1 over 4. That's 10 over 4, and that's 2.5. A location. Yep, 10 over 4, 2.5. For quartile 1. And then we can do 3 lots of n plus 1 over 4, which, if you think about it, the previous answer was 2.5. This must be 3 lots of that, so 7.5 location. Because you're multiplying that previous answer by 3. And that's the location of quartile 3. If we run those, we do a bit of counting. We've got 1, 2, make sure the numbers are in order. Yep, they are good. So 2.5 is the difference between 9 and 12, like the middle. So 9 plus 12 is 21, divided by 2 is 10.5. So 10.5 is quartile 1. And then 7.5, let's go. 1, 2, 3, 4, 5, 6, 7. So it's in between there. 24 plus 26 over 2. That's not bad, is it? It's 50 over 2, which is 25. And the question asks for the interquartile range. So we're going to do IQR, which is Q3 take away Q1. And 25 take away 10.5 is going to be 14.5. Yeah, that'll do. Okay, so that's roughly, descriptive statistics. They are things that we calculate. Like, what is a statistic? A statistic is something that is calculated from the raw data. Okay? It's very different from a population statistic. It's only to do with something we've collected. Okay, so it's only from that sample that we collect. Okay, let's look at a different topic. Probability. Really important underpinning of everything. So insurance companies will use this a lot, obviously, to predict accidents or natural disasters, and they'll set premiums and design policies based on being able to make profit, but also making people reassured about the future. And supply chain management. Companies use probability to predict delays in the supply chain and plan for contingencies. This is used a lot, actually. So some more advanced Bayesian probabilities are used in a number of processes. Like, what is the probability of someone doing something given that they've already done X or Y? Very big, and it's powerful. Marketing will use probability to predict customer responses. So in the same sense, you can, in sales, you use Bayesian as well, but to optimize their strategies. So really, really important stuff. Let's build up with some questions. A bag contains 4 red, 5 blue, and 3 green. What probability of drawing a red ball from the bag? Okay, so really basic. We've got to start somewhere. We've got to know what we're doing. So what is a probability? A probability is written as a giant, uppercase, not a giant, exaggeration, P red. Now we don't need to write red, we just like abbreviate it to the least amount possible. And we're looking for the number of successes divided by the total possible. Which, if we were putting our hand in there, a success would be to pick out a red, and we've got 4 opportunities to do that out of a total of 9 plus 3, 12. And we cancel that down to be a third. Okay, what's the probability of drawing a green ball? Same thing. Probability of a G is equal to 3 over 12, which is a quarter. It kind of makes sense because a quarter is smaller than a third, and there's less of them in there. If 2 balls are drawn one after another without replacement, what's the probability that both are blue? So we can just call this both blue. And I think what we're picking up on here is without replacement. So this is actually quite an advanced concept. So not easy question. I'm going to write this down here that this is conditional. Something happened, it's affecting the second choice. When we're asking for 2 things to happen, well, that ghost is there. When we're asking for 2 things to happen, it's a bit like saying blue and blue, okay, on the caveat that we don't replace. So what's the probability of getting blue the first time when nothing has been displaced? We've got 5 out of the 12. But when we go to, we didn't replace it, we go to pick it out again, we're going to end up with 4 blues this time because the blue has already been taken out and there's 1 less overall. So that's 4 over 11. So you've really got to slow down and think about what has happened before you write down that second fraction, and then looking for the denominator to decrease by 1. If you want these 2 events to happen, and means multiply. So with these 2, we multiply the fractions and we get 20 over 121. Wait, 120, 132. 10, 120. Yeah, 132. This pen isn't writing. Come on now. 1, 3, 2. Which does cancel down quite nicely. We could divide by 2 to begin with, which is 16 plus 50, which is 66. And we can divide by 2 again. And that was where we stop. Okay, so we've arrived. Where to next? A die is rolled twice. So there's not much to this, so we're going to have to interpret what we know about dice. So a dice is rolled twice. What's the probability of rolling a 3 on the first roll? Okay, well, the probability of a 3 on the first roll is essentially 1 out of 6. Which, pretty basic. But what is the probability of rolling an even number on the second roll? A little bit more complicated. So an even number on the second roll, we're now focusing on whether it's an even or an odd. So the probability of even on the second one is the probability of an even and even, because that will be like a probability of even on the second one. Let's move this over here. And there's another scenario where it was odd first. But there's not another scenario, because it's either even and even, odd and even and odd, well, that doesn't count, or odd and odd. So these are the only two situations that work for us. And if we're talking about rolling a dice, well, evens, there's probability of even is a half. So what do we have? We have the probability of an even and an even as a half times a half added to a half times a half, which is a quarter plus a quarter, which is a half. There you go. So we're using the probability theory very well, but an obvious result in the end. Okay, what is the probability of rolling a 2 on the first roll and a 5 on the second roll? Well, the 2 on the first roll is a very specific situation, which is kind of cool. Probability of a 2 is going to be 1/6. And a 5 on the second roll, because these are independent events, we can just say probability of 5 is going to be a 1/6 as well. So the probability of 2 and then a 5 is equal to 1/36, which is 1/6 times 1/6. Okay. In a game store, there are 12 video games consoles in cabinet A and 15 video game consoles in cabinet B. In cabinet A, there are 4 PlayStation consoles and 8 Xbox consoles. Okay. In cabinet B, there are 6 PlayStation consoles and 9 Xbox consoles. Emma randomly selects one console from cabinet A and one from cabinet B. Calculate the probability that the 2 consoles selected by Emma are of the same type. Okay. Of the same type. So we could say that we have different events here. We could have that she picks PlayStation in A and a PlayStation in B, or an Xbox in A and an Xbox in B. Those are our 2 situations. And so we're interested in those 2 being the same. And therefore we got a little bit of calculation to do with an addition at the end. Let's go for it. We're going to call Xbox probability of X. So what's the probability of X and X? And then in the other console, the probability of PlayStation and PlayStation. So we're taking one from cabinet A, which is PlayStation. Now the probability of a PlayStation is 4 out of 12 in that one. And then if we go to our second cabinet and we multiply that one by whatever the probability is of a PlayStation there, which is 6 out of 15. So the only scenario where we're getting a PlayStation twice is PMP, which is 24 out of 12 times 15. Wait, that's not right. That's it, 180. We might want to simplify that just to make our life a little bit easier. That's 2/15. And then we'll do the same with the Xbox. So if we're picking our first one out of cabinet A, the chances that it's an Xbox is going to be 8 out of the 12. And out of the second, it's going to be 9 out of the 15. So 9 times 8, 72. 12 times 15, 180. And we can cancel that down to be 2/5. Now the question, if we refocus, is what's the probability for the two, like that they're the same type? So we've gone through the two situations where they're the same type. So we need to write down the probability that they're the same is going to be equal to the probability of x and x add the probability of p and p, because both of these situations are going to work for us. And when we ask about which one's going to give us a win, it's this or this. And or relates to an addition of probabilities. So that's going to be 2/5 plus 2/15, which if we convert this left-hand fraction to 15ths, that's 6/15 plus 2/15, which is 8/15, which is actually really nice to write instead of the decimal equivalent, which is 0.53 recurring, which is not very nice, not very useful. But the decimal at least tells us it's more than half. So that can be really useful. But 8/15, there we are. Okay, we're going to take a 5-minute break now. Actually, should we do it now? Are we at the end? No, we're not at the end of probability. We'll take a break at the end of probability. Only one more to go. So, a local electrical store running a game to win a prize. Okay. This is like what's happening near me right now. So you buy stuff and then you get this little token to play a game to win a prize. I've been playing every single day. I'm pretty sure I should win. But when I asked for the statistics on how many people that have entered, they couldn't tell me. So I don't know my chances. Write down 2 conditions. All right, so actually let's read it first. You spin a fair 5-sided dice. We probably want a little handle on that. So it's a pentagon. Like that. And then, you know, the little spinny thing and the poker out the back. Not bad. I like a focus on a diagram myself. Let's color that in so it doesn't look like it's silly. Okay. Already looks like it's silly because it doesn't match up, but it doesn't matter. I'm happy with that. So it's a 5-sided spinner, and typically when you spin this, it's going to land on either one of them, and it's going to be fair because it says it's a fair. So that means that each probability of getting each number, which is 1 to 5, is going to be 1/5. So it's a uniform distribution. Uniform distribution means the probability is the same for all outcomes. Okay, so probability that x equals 1/5 in all cases. Maybe that's too much. Let me just write this. No matter what x is, if x is 1, 2, 3, 4, or 5, it's always a 5th. Okay, so what makes this a binomial? It says here, write down 2 conditions that make this binomial. Well, if you're like spinning this fair 5-sided spinner 4 times, how many times you're doing it is fixed. So we can say that there's a fixed number of trials, which is 4. And then we're talking about the game counts the number of 5s. So we say that there are 2 outcomes. Five or not. And there's also this idea that, I mean, I think we could, I'm just throwing another one in there that always is a winner. They're independent trials. Okay, so one roll or spin is going to be different. It's not going to affect the other one. So those are 3 conditions for the binomial, which are really strong conditions, and we'll leave it at that. So whenever we've got something we could model with a binomial distribution. And for a binomial distribution, we need 2 of those. So to calculate the probability that all of the rolls will be a 5, we can use the binomial distribution now, because we've said, yeah, it looks like we can model it that way. So with the binomial distribution, we have n equals 4, and the probability of success is equal to 1/5. And we want to calculate the probability that all of the rolls will be a 5. So in this situation, we could use the formula. And it's actually a very difficult thing to do without the formula, because there's a lot of scenarios that could have happened. But in this case, it's pretty straightforward, I suppose, because it's all of them are. Now, if n equals 4 and p equals 1/5, it's actually the formula becomes quite straightforward. It's the number of successes, so the probability of success to the power of the number of times that we are going to be successful. So 4. So the binomial distribution comes from the idea that if we have 4 trials and we've got 1 success and 4 failures, and the probability for each of those are the same, let's call it 0.1. No, a nice fraction actually. 1/4, because it's different from what we've got. If the chance of getting a success is 1/4, then the chance of failing is 3/4. Right? So all of those are 3/4. But it doesn't matter if that was in a different arrangement, like say the second one was a win, because you've still got 3/4 times 3 and 1/4, and you're going to be multiplying them together. So it's the same result for all those scenarios, just like there's 4 different ones of them. And so, like, the interactions are where we have to use like the formula properly. In a situation where there's only one rearrangement, in our case, it's all of them the same. So the probability that we win on all of them, there's only one way of doing that. And that's where we have 1/5 4 times. So in that case, we're going to have 1/5 to the power of 4 is going to give us the probability that all are 5. I'll make sure I do this in a fraction form. That's 1/625. It doesn't make much sense doing it as a decimal here, because it's very small. But if you were to look at 1/625, you know that's not very high chance. Actually, that makes a lot of sense, because you don't have much chance of getting 4 in a row. It's actually quite difficult. If you ever sit down to try and get 4 of a particular number in a row, it's very unlikely. So it does make sense. So in that situation, we can use our understanding of the situation without using the formula. But when we have this situation, to win the smallest prize, you need to get just 1/5. Calculate the probability that at least one of the spinners will be a 5. Okay, so looking at that for a second, digesting it, at least one of them will be a 5. That's pretty tough. That means the probability that x equals 1 plus the probability that x equals 2 plus the probability that x equals 3 plus the probability that x equals 4. That's essentially it. So there's a lot to calculate there. But what are we missing? If I talk about the probability that x equals 0, then I know that all of that adds up to 1. Because if 0, 1, 2, 3, 4, every single possibility. And that's the golden rule in statistics. They all add up to 1. So there's something very special that we could do here. We could find the probability that we get none. Probability that x equals none. And this would be really advantageous because if we knew what it was, we could take it away from 1, and that would be what the rest of them add up to. So let's set about finding the probability that x equals 0. What does that mean? No success. And the probability of no success, it looks like all fails. So just like up there we had all fifths, that's going to be 4/5 to the power 4, because it's the fail 4 times in a row. Fail and failed and fail and fail. Not the kind of number we like to calculate in our heads. So calculators out. 256 over 625. Do we think it's more likely to win 4 times or more likely to fail 4 times? I know what I like to think. Unfortunately, it's very likely to fail. There's many ways to fail. There's many ways, it's more likely that we won't. Because when you're spinning that spinner, there's the option of getting a 1, 2, 3, or a 4 that's going to get in the way. There's a lot more of that. And so if you're only relying on the 1, look at the chance of getting that, like at least a 1. It's not too bad. If you're talking about failing, it's a lot easier. But now that's out of the way, you can see this distribution is very bottom heavy, right? Very bottom heavy, because x equals 0 on its own is near enough half. But that makes sense, because to get a 5, it's not the majority of the option, right? So now let's finish this and say, well, the probability that x is more than or equal to 1, so that's at least 1, is equal to the whole, everything happening, which is 1, take away the probability that x equals 0. Okay, because if we take away the 0, that's going to be the 1, 2, 3, and 4 that we're after. And so we take that number away from 1. We do 1 take away 0.4096. And we're left with 0.5904. And that's the probability of getting at least 1. Which actually isn't too bad, is it? It's more than half. Okay. Now we're going to take a break. 5-minute break. Time for a drink and a biscuit. Okay, here we are, back for the second half. I'm actually hoping it won't last a whole half. I'm just going to turn my heat pump off. It did help. It's pretty cold otherwise. Okay, where are we at? It's good to have a break, everyone. Make sure you have regular breaks. Regular breaks. Okay, we're up to number 3. So, data cleaning, skew, and distribution. I'm not going to read through it all. I'll leave it up there for a second. Market analysis. So, you know, when you're looking to optimize your autocorrect, looking to optimize market campaigns, definitely used here. Got to collect data set with customer profiles. Data science, 100%. You have to have very strong data cleaning skills. Otherwise, the conclusions that you make have very big implications. Environmental science. Polygons. Frequency polygons. Human resources use them all the time. Can't really get away. What is this? I must have the American dictionary turned on. Finance. Definitely need it. If we're looking at skew and finance. And in customer services, we look at standard deviation to look at inconsistent service levels and skews, and it's pretty cool. So all of these situations in real life, people would benefit from having a good understanding of such things. Right, look at this data. Oh my goodness. What's wrong with the data? Yeah, so the question is, like, what is it that, what does it say? Give all the reasons why the data will need cleaning. So what's going to cause a problem here? Can you see some? I'll give you a few seconds, because if you only just seen it, you only just seen it. Yep. Okay, there's probably enough time. Shall we? Let's highlight all of the problems. Blue. Actually, not feeling blue. Blue. Green's fine. Okay, so here's a problem. Missing data. We call it null data. Okay, so we've got missing data. Gosh, quite a lot of it. Is there a row that's free of this problem? Everything else seems okay in this on the left. They all seem unique. The names seem fine. Just identifies. The order date. Oh, all sorts going on. Look at this. We've got the order written, the year and the month and the day. Fine. But here, the other way around. And that's not going to fly. And neither is this. It needs to be... Oh, actually, no, that would be... Yeah, that's a problem because it's a different format. It's like a forward slash instead of a dash, instead of a hyphen. So that's not going to work. Month. Yeah. Month. Yeah. Month. And 2029. That's obviously the future. Oh dear. That's not going to go at all. Product ID. Oh. No, that's okay. We can have the same product. You can have people buy the same product. As long as it's the same price. Yeah, that makes sense. Yeah, same price to 15.56. Okay, everything seems fine in that row. See anything obvious? Quantity. -1. I could bring about the idea that -1 means it's possible it might be tracking refunds. But in this case, it does seem to stick out here. We need to double check it. Sometimes if we double check it, it's not a problem. It's fine. 3, it's got to be the same format. Otherwise, we're not going to be reading it and calculating with it properly. It's going to have to be a proper number. So that's going to have to change. Now, in the case where you do have data that's a problem, what do? You either go back to the person that you got the data from, try and change it for the better, or you change it because it's really obvious, or in a case like some of these, you just have to get rid of it. So you're going to have to make that call based on what you're trying to achieve. But let's keep going. Price. Free is not a problem. We're going to put 0. Otherwise it won't recognize the input. Total price. You could check that these actually work, because -1 times 1550 should be -1550. 3, yep. 2, yep. 1, 2, 1. There's a problem. It's got to be numerical. It's got to be the same as the rest. Don't see any problem with the calculations. They seem fine. Oh, that was really sneaky. Look at this one. That's not going to compute because you're looking for a particular format and then you run a code that will say, look for this format, and it's not in the format. You're going to have trouble. And you're like, error, and you don't even know why. Okay, there's another error. And there again. Oh my goodness. Is there anyone safe? Is anyone safe? It looks as though there is a safe one. It looks as though this line here is safe, and so is this one. And so is the top one. Now, if there's something there I've not spotted, it could be John Doe. There might not be anything wrong with that. Yeah, it seems okay. So you've only got 3 that made it through there. So give all the reasons why the data will need cleaning. So you've got missed data, you've got the wrong format, you've got impossible values. All of the problems. What do we think? Well, we need to handle those nulls, don't we? The fact that we've got none. Just trying to make sure there's nothing. Yep. Oh, and I suppose when it comes to writing 3 and 50 and 3, those need to be numerical. And a valid email address, of course. Okay, cool. The data is now cleaned and presented in the following group frequency table. Lovely. Use linear interpolation to work out an estimate of the median price of sales. I love this question. I love questions like this. So in this example, we have to find the median, which is the middle number, but we don't know what it is. Look at price up here. Price is a number. But down here, how do you know which one there are? There's 18 in between 0 and 10, 32 in between 10 and 20, but you don't know what they are. So you have to have an estimate and a whole method about how we're going to get there. Now, I've got my method here. You've got your method. If the one you're using so far doesn't work for you, you could try this one. But this is pretty much the standard administered method. It's all based on fractions or proportions, as you will. And we're going to find the middle number, essentially. In order to find the middle number, we need to know how many there are in total. How many are there in total? 40, 50, 95, 100. So here we've got 100 data pieces. And we said that the location of the median the other time was n plus 1 over 2. That's 101 over 2, which is the 55.5 person. Wait, why is it 55? No, it's not. 50.5th location. And in this case, we need to count up. Now I could put 100 down the bottom there, because I might want a cumulative frequency column. So it's very common. It helps a lot of people see the problem. I don't need it myself because it doesn't really help me see. I don't think. Anyway, 40, 50, 95, and 100. But I guess it's kind of useful in a way. So we're going to get the 50.5th person, and by the time we got to here, we're up to the 18th person. Okay. So there's the 18th person is at that line. And then if we carry on to this line, we're up to the 50th person. And so what we're talking about is the 50.5 person being in this group here, just in. So by the time we get to the end of this next section, we're up to 95th, so that's too much. So it's in between here and here, which is 50 and 95. Well, how far in is it? Well, this is where we draw a diagram. And we say that if we're going from 50 to 95, that would be the same as, like if we keep it in linear proportions, 20 to 30. There'll be a point that we go in that would be the same fraction down here as it is up here. Now we actually do know how far we've gone in on the top. It's the 50.5th person. Now this is theoretical because we're going in between the lines here. This is linear interpolation. So we're going to use it, even though it's not a whole person, we're going to use it as it is, as a fraction. So what we're looking to do is find this distance here. Oh, hello. I mean, sometimes I do want an arrow, Microsoft, but right now, just the line, thanks. We're going to find this distance here, which is green, as a fraction of the total length. And we're going to use the fact that it's the same length as the section that's right underneath it, that represents how far we go into 20 to 30. There's a whole formula. Well, it's pretty obvious when you see it. It's the distance of green. So 50.5 take away 50. That's going to give us. It's going to give us the answer for the green value, distance. And that's going to be divided by the total, which is 95 take away 50. That's that whole length there. And you can see then if you did that, sorry, you did the green divided by the total length, it would be a proportion of the total. And that is equal to a similar thing that's going on down the bottom. Now this bit is what we want to know. We'll call it x. So it's equal to the difference between x and 20, which is the yellow, divided by the total difference, which on the bottom is a 30 take away 20. So we're setting these up as an equivalent fraction sort of thing. And this is going to be computed. So 95 take away 50 is 45. And 50.5 take away that is 0.5. Can't do much with x minus 20, but 30 minus 20 is that. If we times the left-hand side by 10, alright, I don't really like working right to left, but so let's move this over here. I'll move this instead. Okay, so we'll multiply both sides by 10, so we get 5 over 45 equals x minus 20. With a little bit of calculator wizardry, we're going to have 5 divided by 45, and we're going to plus 20, so that's going to be 20.1 recurring. Better to write that as a fraction if you want the exact. And this is going to be what? Is it price? The location of the median has now then been translated to price, which is how far it went into this range. And you can appreciate it's just an estimate. It's 20.1, like a tiny bit in. And if we write that in terms of real world, then we can call that £20.11. Because it does relate to a price, and that kind of grounds it, kind of makes sense. Now, we said that the 50.5 went only a little way into this section, so we should only go a little way into 20 to 30. And we just so happen to calculate the precise amount according to the proportion. All right, so £20.11 is an estimate for the median. The frequency polygon for the prices has been drawn on the grid below. Comment on the skew of the distribution. Distribution of the prices. What does this mean in the context? What does it mean indeed? Well, how can we analyze this? We would say that the highest frequency occurs in the 20 to 30 interval with a midpoint of 25 by the looks of it. So this is the highest point. We will start to write this down. So we'll say highest frequency is between 20 and 30. Maximum is 25. That's not very clear, is it? We're going to say that the midpoint of range is 25. Why do we use the midpoint? We use the midpoint because we're estimating. Yeah, we can't just pick any particular one out. We've got that middle. And so that's really important to find that middle price height. There's no frequency in the 30 to 40 range. Okay, so that accounts for this here. No frequency there. And yeah, I guess the last thing, the frequency drops significantly, 40 to 50. So this whole section here is dropped significantly. Now, therefore, there is a case to say the majority of it is around here, and there's a little bit of a tail off to the right. So how would we sort of begin to draw that a way that I'd be happy with? Something like this. I don't class that as a massive tail. I mean, perhaps you could argue with me and draw it slightly different. What we're talking for skew, ideally, is something that looks like this. Right, so that's definitely a tail on the right for a negative skew. And what's it doing? Silly thing. And then if we're going to talk about a bell curve, that's even, or it could be on the other side. So this one being positive, negative, even. Which one is it? And there's a lot of interpretation when it comes to this, so I'm going to go with the fact that this is quite central. I would say that the polygon is quite a nice way of showing distribution. Hold on 1 second. There. It's quite a nice way of showing distribution, and I would say that you could get away with saying that this is an even distribution. It's not too far off. I mean, you're talking about the left-hand side being a little bit higher than what happened over on the right, but I don't think it's enough to say that you'd lose marks by calling it a nice even distribution. That said, if you wanted to say that it was a slightly positive, you would also get away with that. So we can leave it like that. And what would this mean in the context? If it means anything at all. It means that the prices are normally distributed around 20 to 30. So we could say that the most prices are between 20 and 30 pounds. You can find that quite useful, actually, as a sort of target. You could confirm that with the median, which we found the estimate to be just in the 20 range. And this would confirm, it would support, really, wouldn't it? Because you've got something in the 20 to 30 range, but it was closer to 20. So that would support the idea of there being a slight skew. Now, the way to really get around this is to calculate skew. And there are a number of methods of doing so. Not that we're going to go into that in this particular one, but just by observation, we're looking at the graph here. And you could calculate the skew as an actual number, and you could put it into bandings, but even then, you've still got some interpretation as to what's strong and what's weak. Yeah, so we'll leave it like that. Okay, next is sampling. So market research is using sample techniques all the time. Whenever you want to get a sample, you're going to use these techniques so that you get a good sample. And they will, in marketing, use it to ensure that there's a good spread across the entire population. At the beginning, in the intro, we talked about randomly selecting our samples, but not necessarily getting a representative example. Like, for the example, where they were all red, doesn't represent the population. That's no good. And so what we're looking for is instead to manipulate the random a little bit so that we get something that represents everyone from different demographics. It's in epidemiology as well. We've got public health officials that are using these data about disease to measure the prevalence of it in a population. And the sample is used to ensure that different subpopulations are adequately represented in the health studies, because otherwise they won't be heard, and they're very important, especially when it comes to health. The way we sample is very important. A research institute has 72 scientists divided into 3 departments: physics, chemistry, and bio. The institute is conducting a survey on workplace satisfaction and intends to gather opinions from a sample of 360 scientists. Each department has scientists working on different research projects. The institute's management proposes that 3 sampling methods could be used to select scientists for the survey. Let's read them. We'll fun being the boss and just getting to decide which one is best. Method A. The management will choose 5 scientists from each department, ensuring a representation from various research projects within each department. What do you think? Sounds pretty fair. Yes? No? I would say that if they're going to do that, they seem to have different stratums, which are groups essentially, where scientists are going to be selected in fixed numbers from each department. So it's kind of a method like stratified sampling. And I guess it ensures that there's a representation from each department. And it doesn't talk about going on and saying, you know, how you're going to pick them from within each research project, how you're going to make sure it's various research projects are going to be represented properly. So there is a limit to that. It does make it suitable for understanding satisfaction across different scientific departments. There's less clear about different disciplines, but it does help capture somewhat the diverse perspectives from within the institute. Okay. Method B. All scientists are assigned a number from 001 to 072. There are 72 in total, aren't there, people? Starting with the number 007, for some reason, and taking every 9th scientist, so that the sample consists of scientists numbered 007, 016, 025, and 07, etc. I know this one. This one's called systematic. There's like a regular system to it. So in the previous one, we put them into groups, and I'm assuming that all of those groups, which are the departments, have an equal number of people, say 30 in each one. And therefore we take 5 from each department. So we have a sample of 25 in the end. And the 5 from each department have been taken. So we're getting a representation across the departments. Here, we have lined everyone up. Oh dear. Let me use the built-in function instead. That might work better. Give me a little rectangle. Oh well, never mind, that'll do. So we've lined everyone up, and we have seen how many people we want to take in the sample. So 72 people are here. How many people do we want to take in the sample is the question. Oh, it's actually 360 scientists. So they... What? That doesn't make any sense. A research institute, 72 scientists divided into 3 departments. The institute is to survey workplace satisfaction to get the sample of... That can't be right. 360. I reckon it's something like 12. Or we could say 25, because we've already used that. Each department has scientists working on different research projects. Okay, fine. So we actually want a sample of 25. A little bit harder with these numbers, but we can do it still. That would make sense in the other department. There was not 300, there's not 30 in every department here. Can we divide that by 5 nicely? No, not really. Let's make these numbers real. So 72, let's make it a really nice department, eh? Make the numbers work for us. Let's say there was 6 departments. And if there are 6 departments, that means there's 12 people in each. And had to get 25, we're going to have to take 5, 5, 5. That's 5, 10, 15, 20, 25. Maybe not actually. It's going to be 4, 4, 4, 5, isn't it? Let's do the 5 first. 4, 4, 4, 4, and 4. So that's 25. Now it's not going to be perfect. We have to say 1 extra from there, or we just take 24 and we're representing each department the same. With 72, and typically we round it anyway, so yeah, it'd probably be all 4s. With the 72 here, we're saying everyone's got a specific number, and we want 25 people, so we'll say 72 divided by 25, and this is not going to be a very nice number. 2.88. So we're going to go up every 2.88 persons. So we're going to round that to 3 people. So we're going to go every 3 people until we get to all of our 25. And if we land on the same person twice, we're going to move on, discard it, and keep going. And where do we start? We start from a random start point. So the random number generator will give us here. And then we're going to go up every 3. So 1, 2, 3. 1, 2, 3. And every time I color in, that's a person that's been selected. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So we've gone up and we've got our randomly chosen systematically. The problem with doing this is that if you have a system like a conveyor belt and I don't know, let's try and draw this. So there's a machine that looks like this, and we're trying to see if these little spikes produce a good product. But imagine that this spike is broken. Okay, this is a broken spike. And as it turns around, this one creates a good one, this one creates a good one, this one creates a good one, and then boom, this one doesn't. This one's good, good, good. So what's going to happen is you're going to get 1, 2, 3, 4, 5, 6 good in a row. 1, 2, 3, 4, 5, 6, and then across. 1, 2, 3, 4, 5, 6, and then across. So if you're doing it with your simple systematic sampling, just like this, and let me put another cross in there, and your random start point is here, and you're going to pick every 7, you're going to pick only the bad ones. So the sample is prone to bias if regular errors in the system. Okay, so that's a production line example of where the regular one that gets picked matches the regular error problem. But generally, systematic sample is considered pretty good. You've got a random start point. It can be efficient. In this context, though, it may not ensure the representation from all departments. Clearly, there are different researchers within each department. You could get more from one department than the other by the looks of it. You could miss out on capturing the specific departmental nuances or project specific satisfaction levels, for example. All right, method C, what's this? Each scientist in department will be given a raffle ticket, and 10% of the number of scientists in each department will be chosen at random by drawing raffle tickets from boxes. 1 box from each department. So 10% of the scientists in each department were chosen at random. Okay, so we're taking a proportion, a representative proportion of each of the naturally forming groups. But this is cluster sampling. Pretty sure it's cluster. Cluster sampling essentially it's where clusters, which in this case would be departments, are identified, and then a random sample from each one is like taken to represent them. And in other examples, it may be different areas of the country would be clusters, or in a football league, then the different teams would be clusters. And you want to make sure you got the representation, a certain percentage from each one. However, like, it's all very well, and it feels like it's effective with the departments. And if the departments are, I guess, like pretty samey and homogeneous, then it's okay. But it could overlook differences between different research projects within the departments, I would say. Potentially skewing results, especially if satisfaction levels vary across different projects. So we're not necessarily taking into account everyone. So I guess in conclusion, method A seems to be the most appropriate sampling method, because we're taking into account all those different groups in the right proportions, and it minimizes bias and provides a balanced representation of opinions. So if I had to pick, I'll go for A. Okay, and finally, data representation. So obviously this has been a long time in the making. This whole this live stream has been very long. So we're going to leave it at this last one. Let's have a read. So data representation is used, a couple of examples, by real estate agent analysts in like histograms or a number of different things within prices of market, time series and trends and stuff. Education uses all sorts of graphs. Histograms are one of them, but just to identify performance and trends, so time series as well. And this one is distribution. So the following stem and leaf diagrams give information about the heights of students in two different schools. So actually we're going to go ahead and draw this on the same thing. So I'm going to need a wee bit higher, like there. And we can go out the other way, because we have the same stems. And this is typically how we represent the two stems, like side by side. We can see that in this case, there seems to be more of a sort of a modal point there. And this one a little bit more skewed to the right, because we haven't got data for 14. But no real particular mode there sticking out. So we get rid of that. It says the heights were all measured at the same time. Okay, fine. Compare the average height of the students in group X with the average height of the students in group Y. State clearly the value of each average used when making your comparison. Okay. Well, we're looking first of all for mode. Why not? So in each row, we're looking for the same number occurring twice. 0, 2, 5, 8, 0, 2, 5. They don't. Neither of these have a mode. And so we can't look at mode. The next easiest one to look at would be median. So median is the middle point, right? So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 data points for group Y. 1, 2, 3, 4, 5, 6, 7, 8, 9 data points for here. So we can do a quick, we'll do it over here. We'll do a quick 9 plus 1 over 2, 10 plus 1 over 2, which gives us the fifth location, the fifth number, nice and easy. And this the fifth point, fifth location. I always have to write location, otherwise I might end up writing down that the answers are 5.5. The fifth location, starting from the bottom, is 1, 2, 3, 4, 5. So the median for group X, should we call it median X, is going to be the fifth, which is 163, versus median of the Y, which is 5.5. So 1, 2, 3, 4, 5.5. So it's in between 165 and 168. So the median of Y, I would have to, although we do have to calculate something pretty difficult sometimes, at least we've got a method and we just need to worry about those calculator skills. Okay, so the median of Y is 166.5. So we are told to compare the two. So according to the median, we would write 166.5 is more than 163. And to be really scientific, we'll say there's evidence to suggest that group, which is more, don't get it in a twist, and that's why I always write these little X's and Y's. Y is, what's the situation here? Stem and leaf grams, 2 schools of heights. Okay, then group Y is taller in general, right? So there's some evidence to say that. We could go on and find the mean as well, but it's not like, I guess it's not as quick. So if it did go on and find the mean, then like that could tell something else. What I'd like to look at is how sure we can be just because the median is above the other one, which is quite a big deal actually. Yeah, so in that case we might want to find quartiles. So let me get my mouse here so I can get myself some space. We've already got the median, so let's find the quartiles of each. So it's going to be n plus 1 over 4, 3n plus 1 over 4, and it was for 9 and 10. So 10 divided by 4 is 2.5, and turns out it's 7.5. And this one is 10, which is 11 divided by 4, which is 2.75. And times that by 3, we've got 6, 7.5, 8.25. Okay, so they're the locations of the lower and upper for us. And we've also got the median of both, all right? So let's actually write those. So we've got quartile 1, quartile 2, which is the median, and quartile 3 for each of these. Where are they? 163 and 166.5. So 163 is on the right. And 166.5 for X. Okay. So the 2.5 for X is going to be 1, 2.5. So it's in between 150 and 153. So in between 150 and 153 is 151.5. And quartile 3 is the 7.5. 1, 2, 3, 4, 5, 6, 7.5. So in between 169 and 173, which is a difference of 2. So we just 4. So we just add on 2. So we get 171. Do the same with this one, 2.75th location, 2.75th. So it's right in the middle of 155 and 160, which are 157.5. And the upper quartile is the 8.5. So 1, 2, 3, 4, 5, 6, 7, 8, in between 172 and 175. So the difference of 3 divided by 2 is 1.5, added on, 173.5. Okay. In this case, we can sort of look at this as a box plot, if it helps to draw it, I suppose. But it's where these three overlap is what we can really, it gives a hint. So on a scale, I can roughly see that the one on the left is slightly lower. So let's just draw a box. They're pretty equidistant, 15. Okay, it looks something like that. Let's call it 151, 166, 171. And that's for X. For Y, we have 157, which comes in there for the lower quartile, 163, and 173, like this. So that's pretty tough. So the difference between those two medians, to say that one is significantly away from the other, there is a measure, as a bonus I'll disclose, there's a measure that we can take where we take the overall visible spread, and I'll just write in 173. The overall visible spread is 173.5, take away 151. Which leaves us with 22.5. And this overall visible spread, depending on how many we've got in a sample, how many do we have in our sample? Not that many. Not that many. So we can divide that by 3, which is 7.5. So the OVS over 3 is 7.5. The difference between the means is 166 take away 163, which is 3. So that's the difference between the means. So when we're talking about whether this difference, is it significant, it has to be bigger than this. Okay? So if it isn't, then we can say that there's not really a difference. So in this case, 7.5 is much bigger than 3. Therefore, no significant difference between the medians. Because what are we looking for? We're looking for the medians to be far apart. And what is considered far apart, to say that one's bigger than the other, is where the overall visible spread divided by 3. And that's what's considered significant. We're looking at the overall visible spread, which is that whole length there. And if we split that into 3, that's considered the distance needed between the medians to say that there is a difference, big gap. And as you can see, the difference between those two yellow lines is definitely much bigger than the difference between those two medians. And so this is called making the call. But that's one way of telling whether there's a significant difference between the two. So yeah, so we're just using averages, but to extend the idea of whether that average was significant or not, we're using the idea of an overall visible spread. Oh, hello. Send to me. What topics are you going to go through after this? Well, for me, it is nearly 2 o'clock in the morning. So that's me out. But please do suggest what you want to see. I think I'm going to need to do a part 2 to cover everything. It was only meant to be a general recap, a little bit of Q&A. But I'm happy to do another one. You've not got long till the exam. So I can definitely whip something up. What would you like to see? And just in case there's a delay in the sound, I will type that in the chat. Yeah, I think I put these together. It took about an hour. Put some questions together that were very similar to the spec. Looked at a few past papers. Thought of some real life scenarios where they would be used. Data cleaning, very important. Interpolation. Some of the tricky skills that we really don't like, people get them wrong for sure. Probability does get pretty tough when you start using conditional probability or the binomial distribution. Don't forget your calculator can do this for you. So for example, if you had the Casio FX991EX, which I do have right here, you go to menu, and then 7, which is distributions. And then you go down to binomial. You do have cumulative as well, so that saves time if you're doing multiple inputs, but let's just say you want to do individual inputs. And then you're going to click on variable. And then here we go. You get to input x, n, and p. And you probably guessed it. X is probability of x. That's what you're trying to find. That's the x in there. I'll go to do an example, don't worry. This is the n, the number of trials. This is the probability of success. So in the above example, if we had, let's say in blue, you wanted to find the probability that x equals 2, and we had x is binomially distributed with 20 trials and a chance of success of 0.1, then this would go in your calculator as x equals 2, and n is 20, and p is 0.1. What do you get? What do you get at the end? Is 0.2851798,071. I don't really mind any topics as I've been entered into the exam without learning the content. So anything would be, oh my goodness. I still have hope to do well. Yeah, of course. In paper 2, I did okay in paper 1. I'm hoping for a 6. All right, good for you. Good luck. Yeah, I know paper, like, let's have a quick look. What hasn't come up for you? I haven't seen paper 1 yet. Yeah, so paper 1 was on the 5th of June. And Monday's the day. Having a look if someone's put up what was on the paper 1. It doesn't seem that popular. People don't put them up if they're not popular. And we don't get hold of them. Okay, so there's literally a, that's really weird. Okay, somebody has put GCSE paper 1 online, I think. Part 1, statistics, GCSE maths.
They will be looking at one of the...
They had to mask their voice. Yeah, that's too hard to read. Just one of them. It looks like probability trees have already come up. Tuesdays and Wednesdays, something ring a bell about that? Anyway. Okay, median interpolation. So we've done that on this. So we've covered the median interpolation today. That's one of my favorite topics. Where would we do that? Here. So when you're going into the range, that's how you do it. It's about fractions. Calculating outliers. Yes, we could calculate outliers. Easiest way to do that is to go, we could do one type really quickly, which is to go to somewhere where we've done box plots already, or calculated a few of the medians or quartiles. Suppose we could do it with this one, because I kind of started drawing a box plot. I went off on one. So let's do it. Well, it's only a rough, of course, but let's say now we'll put in the minimum and maximum, but we'll not worry about that. So one form of outlier is 1.5 multiplied by the interquartile range. In fact, let's move this up. It's an outlier if we do quartile 3 plus 1.5 lots of the interquartile range. And also, if we did quartile 1, take away 1.5 lots of the interquartile range. So we ask ourselves, like, at what point, if we're going to plot these going off to the edge, at what point is it an outlier? If you ask me, probably around there. But there's a measure, and it's to do with the interquartile range. So we found the interquartile range roughly. Let's do it for y. So the interquartile range for y was 173.5. Take away, what's quartile 1? 157.5. Let's get this accurate. So 173.5, take away 157.5. Oh, I'm in probability mode. I love this calculator. I even love it when I get it wrong. 173.5, take away 157.5. 16, beautiful, beautiful. Okay, so this is the interquartile range for y. And if we multiply that by 1.5, and that's 8 added on, so that's 24. So 24 is the distance either side of the quartiles that would be considered a cutoff point for the outliers. So we've got 173.5 there. We're going to add on 24. So what would that be? Quite a bit, actually. It's probably about here. So if we go another 24 that way, anything past this line here would be called an outliers. Yeah, outliers this way. So this wee guy here is an outlier, and so is this. But those that are not past that line are not outliers. And similarly, the other side. So we've already calculated the interquartile range times 1.5, that's 24. Anything past it this side is an outlier. Now we don't need to do that with drawings, I like to see it. But let's calculate it with numbers. 173.5 plus 24 gives me 197. So for y, gosh, I need some space, don't I? Let's go down here. For distribution y, an outlier is defined as, well, I think we'll do it in 2 stages, greater than 197.5. And then if we go to our lower quartile, which was 157.5, and we take away 24, it would be an outlier on the other end if it was lower than 133.5. So we're going to check the data to see if any of those are outliers. So we have to be outside that range. Our biggest number is 178 and our lowest number is 152. So there are no outliers. So there, we'll just write that. No outliers. And we can do the same thing for the other, and then that's a form of cleaning the data. So we clean the data that way. There's another example of how we define an outlier, because there's many ways. And one of them is the standard deviation, but I didn't get onto that calculation. When we talked about skew earlier, there is a measure of skew as well. So skew is, I think, 3 times the mean, take away the median all over the standard deviation, which I'm just going to write as this. And this will tell us a skew, it will be a measure. And that's like a measure of that. We didn't look into that one today. And the other one, let me think. Thinking about the outliers, what would be classed? I think it depends. I'm just going to look through the spec here. I would class it as 3 standard deviations, but I just want to double check. Sometimes it's 4. At university it's 4. Maybe if I just search document outliers. Okay. Identify outliers by inspection. So just by looking. Comment on outliers. Yeah, there you go. Okay, so I've talked about the interquartile range times 1.5. The other definition of an outlier is where the data is including things like the mean and the standard deviation. So when you have that data instead of quartiles, which it often comes from different types of data, then the definition of an outlier is 3 standard deviations out. And I'm just thinking, do I have any of that today? I didn't do any today. But you have data, 30, 40, 55, 72, 100, 193. And we can say that, let's say the average was 70 and that the standard deviation was 9. Then we would define the outliers as anything past that point. So the upper limit would be 70 plus 27, which is 97. And then the lower limit would be 70 take away 27, which is 43. And then we'd look to see if any of the numbers are outside of that. Clearly there are. So we've got a cutoff point there and a cutoff point there. So according to this information, this and this would be outliers. Would be outliers, yeah. And this is also an outlier. The question is, how do you get your mu and your sigma? And that would be calculation based, but something pretty straightforward probably. Numbers, box plots, calculating risk, cumulative frequency. We've done that today. We didn't draw scatter diagrams today, but they're pretty basic. Let me grab a data set a second. Let me just create one. Won't be long, just program it. Okay, let me get this into this document. Scatter diagram. I call it a scatter graph, but that's cool. Table. I want 1, 2 across, and 1, 2, 3, 4, 5. 11. Okay. So we want 2 columns and 11 rows. So, I don't know, let's just make some up, eh? So, 2. Something like that. Where's my mouse gone? I'll get rid of that first one so we can call it something. We'll call it X. We'll call it the number of hours. It's usually pretty good. And then the test score. Call it score. And we'll go for So yeah, this is the number of hours that people did their study and the test score that they got out of 100. Let's get ourselves some jolly wee squares. And we're going to draw this as a scatter graph. You'll note first of all that this is bivariate data because we have two different variables. And this is person 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Bivariate, meaning we took two variables from each person. Okay, we have to draw this. So scale, modern tech, not bad, eh? Not bad. I'm just going to draw it erroneously at this point, and I'll probably make it up, make it fit later. Back to blue. Now, we're going to think about what the independent variable is here. Do the number of hours is our hypothesis. Okay, so this is a hypothesis. Is the hours going to change the score, or is the score going to affect the number of hours that we do revision? I think we can see that it's the number of hours it's going to affect the score. So our hypothesis is not a question, it's the more hours spent revising, the higher the score. That's our hypothesis. So if you have to make a hypothesis, it's going to be that. Now we're going to plot this to make sure and see if it's true. So we've got probably 1, 2, 3, 4, 5, 6, 7, 10, 11, 12. Okay, cool. So that works. And we can plot 3 and height of 100. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh my goodness. Did I get lucky or what? Make sure you draw the lines on the line. Number 1 error. 10, 20, 30, just to give an idea of what scale I've got going on. And we're going to go through in order. So 3, 55, 40, 50, 60. And I'll probably circle it as I go. 360. 565. Oh, there. And 670. 675. 588. Could possibly be an outlier. Maybe not enough. 791. 8 and 98. Golly gosh. And we got a 9. We got a 9 in 98 as well. And we got a 9 in a 100. And we got an 11 and a 100. Okay, so now we've drawn this, we want to sort of put a trend line in. Now our hypothesis is the more hours spent revising, the higher the score. So we want to see if that's true, and you could call the gathering of this data as sort of some sort of experiment, and we call it the truth, because if it comes from the real world, then it's truth. And the way that we can see what this is telling us is to draw the scatter graph and by inspection see what is going on. Like, is it a positive or negative correlation? Because what we surmised here, the more hours spent, the more higher score, we think it's going to be positive. So by inspection, does our graph show us that? We do want, hopefully, to have the same number of crosses above and below. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It's roughly 5 on the top and the bottom. And I can get my 5 there. I give you some advanced skills in drawing scatter graphs. If you roughly look at the end 2 or the end bunch, and then you do the same for the other side, your scatter graph should go through the middle point of those. So roughly there and in between those two. And then after that point, we want to make sure that we've got roughly the same amount of crosses on top as we do below. So 1, 2, 3, 4, 5. And there's going to be 6. So it's just going to be 6 and 5, and that's just the way it is. So let's draw that there. Another indicator that we have good distribution is that when we look at the shape, it looks like the shape of an eye. So if it's distributed this way, it's what we call binomial. That means that in this direction it's normally distributed, and also in this direction it's normally distributed. And it gives way to this shape of an eye. But this is all extra stuff, you don't need to worry. You also want to think about, are there any outliers? I'm going to say there's probably not any outliers here. Because, I mean, there's a way of calculating an outlier. It's beyond the scope of the course, but there is a way. You might, the only one that I would think you might say is that one, but I don't think you'll get away with it. I feel like if it's outside of this sort of eye shape, then you've got a chance of saying, because this is outside of the scatter. I feel like something there would be an outlier, but I don't think there are any outliers. I'm also wondering if there's any unusual clusters here. Not really. Nearly, this is an unusual cluster, but this is pretty much type A perfect correlation here. It's pretty nicely distributed around, as you can see. So from this, we may be asked to make predictions. Let's go for an orange. And a prediction looks like, I don't know, what is the test score? Of this pen. What's the test score when the number of hours that you put in is like, what haven't we got so far? 4 hours. Okay, and this, just like we did with the median interpolation, is a form of interpolation as well. Because we haven't, if you follow up from 4 hours, and we should probably label that, if you follow up from 4 hours, it doesn't go to a data point that we have already. You can't see that in there. And so because it's in between, we're using the method interpolation. Okay, so it's interpolation. And then we can guess, we can say, what, 64? And that's our guess, but it is just a guess and it's really rough. And there's other methods. If you're not going to use like standard error bars, then there are other methods such as drawing around the shape of the scatter, and you can get a rough estimate as to the error involved in your calculation. So using green, I suppose, this is our point that we got our information from, but it could have been as high as up there, or it could have been as low as down there. So you could say, if you wanted, 64, but could be as high as here, so then maybe like 78, or low as like 54. Okay, so there could be like a whole range. You could preface it this way if you want to look at it, because as you can see, for number 5, for example, if we follow number 5 up, we've got a range of possible answers. Neither of them are on the line. One is really high up, one is below the line. So when we make a prediction based on the line, it's quite unlikely that that is going to be the actual result. It's probably going to be around it a bit. So we have to take that into account. And the only other thing is if you're having to make a prediction which is outside, so everything that is in this region here, okay, all of this is labeled interpolation. And that's because it's inside the range of what you have as data. If you go outside, you have to be very careful. If you go outside the measured data, that's called extrapolation. If you're going to make a prediction that way, well, think twice. Very dodgy. Yeah, well done. Sorry, I should look at the comments a bit more, but I know there's always a delay. But you're right, the hours change the score. And the example I gave earlier at the beginning was a good one. We'll come to that in a second. But let's just finish this to say that the hours are the independent. And some people call it the explanatory. And up at the side, the score is the independent, or the response. So whenever we're making predictions, it's always going to be about the independent predicting the response. And the independent always goes on the x-axis. All right, brilliant. So that's that. And let's go back to the introduction. That's a really good example because it's just so obvious that it only goes in one direction. Yeah, here. So as the weather gets warmer, the ice cream sales go up. But clearly, if it were the other way around, it would just not make sense. Like if we all go out and buy ice cream, is that going to make the temperature go up? You know, there's really quite a good one. And then lastly, when we come to this, you have to calculate something called the PMCC. The PMCC is the product moment correlation coefficient. And it gives you a measure of the correlation. So far in this what sort of talk so far, we've gone through how to find it by looking, by inspection. And we can see that it's kind of rudimentary. It's as a guess, really. You're just looking. But when it comes to like a proper measure, the PMCC it's going to give you a number between -1 and 1 on how strong that correlation is. If it's negative, it's going to be a negative correlation. If it's positive, it's a positive correlation. And so PMCC is a calculation that's on the course. Just trying to find it here. Where is it on the course? Spearman's rank is on the course for sure. Oh, no, PMCC won't be required. That's good. Nice. So PMCC is not required. So we've done everything good so far. But this would normally calculate the correlation between -1 and 1. And actually the Casio FX991EX calculator calculates this for you. So if you were in the exam and you wanted a way to double check, oh, I think it's a certain whatever, and you had the original table of values like this, because you can't do it without the table of values. Your calculator can't, for example, look at the graph you've drawn and then interpret it. It has to have the data. It will give you the R-squared value. So PMCC hasn't actually, it's not an issue. You've got PMCC, as you said there, but I'm looking at the specification. I'm just going to paste it in now. And it says here, understand the distinction between Spearman's rank and PMCC. So I'm sure you're probably going to get given the PMCC as a measure if it ever is needed. You're normally going to be calculating Spearman's rank, which just puts them in order of rank, not correlation. It tells you whether two judges, like so Spearman's rank, that's what we're talking about now. So Spearman's rank will tell you whether two judges are ranking their talent. So let's say you've got some singers and they've got their microphones, right? They've got 3 singers. Copy paste would have been good. All right, so you've got 3 different singers, A, B, and C. And you've got judges 1, 2, and 3. And judge 1 puts the rank A, B, and C. The judge 2 says A, C, B. And the judge 3 says B, C. No, let's make it even easier. C, B, A. What you'll find with Spearman's rank is that these two will be fairly high score because they're ranking in the same way. But this one will be totally the opposite to the others and would be sticking out like a sore thumb. And so it wouldn't be a very high score. So you're going to tell whether 2 judges are going to be the same or not. With the PMCC, it's a calculation that gives you the strength of the correlation between 2 variables. So we're looking up at our one here, which is hours and score. And if the PMCC was a really big number, these would be right on the line. If it was close to 0, there would be no trend at all. There would be no line to put. And if it was -1, it would be going the other direction. So there's a whole scale to interpret. We can just plot out some key points, and that will be enough for you to know. So it goes from -1 to +1 and 0. And we'd be very surprised, like the region that would be called no correlation. What do you think it would have to be? Like 0.1, 0.2, 0.4. So anything that is less than 0.4 in terms of magnitude, that's going to give you no correlation, really. You can get away with that. But there's an overlap. So if we're going to go for mild correlation, you can get away with that all the way from here to here. So if we're going to say slight correlation, because you can have positive or negative, that has a range between 0.2 and 0.8. So this would be a slight positive, and this would be a slight negative, between -0.2 and -0.8. So only region where it's strong is here and here. And these are what we would call strong positive, strong negative. Hopefully that clears it up, but it's not straightforward. You see, there's a wee bit of an overlap interpretation-wise, and I'll be honest with you, you could probably go a little bit into there as well, and people let you get away with it, because you're not really... What is strong? It's relative, right? Yeah, there you go. So they give PMCC to you. And if there's a positive nonlinear correlation, both coefficients will be positive, but the Spearman's coefficient will be greater than the PMCC. There you go. What else? Stratified sampling. We did that. Capture-recapture. Bear with me a second. Okay, here is a capture-recapture example. Classic biologist at work. They're always capturing stuff, putting them back. I do find this logic really mathematical, not so much statistical. So let's see if this question makes any sense. A wildlife biologist wants to estimate the population of a certain species of fish in a lake. Oh, yes, classic. We're going to call this Lake Tekapo. I'm going to draw this lovely lake. Let's go off into the distance with some montagne in the background, but that's not what we're here for. So she captures 100 fish. So we're going to take a little sample here of 100 fish. And when it comes out, this is made up of, and she tags them, right? So now all of these fish in here have got wee tags. No, I'm going to learn from my mistakes. I'm going to copy and paste now. Okay, so there's 100 fish with little tags, and they're going to then go back into the the lake, and they're going to disperse. And the theory is that once they disperse and you give them enough time, that the proportions that you've found in this little area are going to be evenly distributed across the rest of the lake. So when you came out and you picked these 100 fish from this section, you assumed that those 100, that they represent the whole lake. Over time, once dispersed. And when we go back and pick another 100, we should see the same. Similar in some ways, but not quite. What we should see is that this little sample is like a scaled down version of the whole thing. And once they have spread into the whole, we would then be able to capture how much there are in total. So let's say that they went to all ends of this little lake. So we, after having this little tag party, they were spread out like this. Nice and even. And then we go and capture another 100 from over here. We can see that we've captured 3 from before out of the 100, and we assume that this recapture represents the entire lake. So if we picked 100 from here, we would get 3. If we picked 100 from here, we would get 3. And it's the second recapture that we assume, because they've dispersed evenly, that it represents the whole lake if we did another 100. So what does this tell us? She captures 100 fish, tags them, releases them back. After allowing enough time for the tagged fish to mix, she captures another sample of 200. And in this sample, she finds 10 are tagged. Estimate the total population. Sorry, just got a message. So if the the first time we did it was like 100, and the previously it was 100, and now it's gone up to 200. We can relate that back to what it would have been and so some sort of a multiplier. So 100 went in. How many was it? 10 were tagged. So that's 5 in every 100. But what does that scale look like? Well, the scalar is 10 to 200. And the original amount was 100. Does that make sense? We're doing the capture-recapture method here. Just checking if you follow so far. It's okay if you don't. I'll just continue in a second if not. Essentially, when we went back out, they've decided to capture 200. Cool. So in that case, because we are talking about the fact that 200 have now been caught, but then there was 10 in that 200, how much would we assume would be in the whole of the lake? Well, if 10 of them made it from the original, that's a factor of times 10, isn't it? And if each of these represent the lake, then that factor of 10 makes 2,000 to be the estimate that we have. Because we assume that this 10 has evenly spread. So you could call them the whole lake being split into even groups of these 10 tagged fish. And if that's the case, then there's 10 lots of that group. And if 200 were picked out, that's going to be 2,000 in the total. There is actually a formula for this. If I think about it, it's the same thing every single time. What would it look like? Something like this. If it's cancelled, yeah. So C would be the number in the second sample. M would be the number originally. And R would be the number of fish when recaptured. Actually, the number of tagged fish when recaptured. Yeah, and then that's pretty much it. So that's the capture-recapture method. If I were you, I would probably memorize that. If you didn't fully grasp it logically on your own because of the way things scale up, and that's pretty tough, we can just lean on this formula. What else can we do quickly? Because I'm actually not that tired right now. I should be. I really should be. We've gone through pretty much box plots. Find the quartiles, draw it on a scale. I even gave you some advanced stuff, so you can look back through this live stream for that. We did cumulative frequency. We've done scatter. We've done stem and leaf. We did stratified sampling. Just did capture-recapture. The weighted mean. I'm not going to do the weighted mean. That's pretty straightforward to look up, I'd say. The geometric mean, that's pretty straightforward to do as well. Standard deviation, that's a formula. You get given the formula. Spearman's rank, you get given the formula. You just got to know with Spearman's rank on the interpretation. Done PMCC. We didn't do Venn diagrams, that's fair enough, but I do have a really good method, a video on Venn diagrams. It's called the Fabulous Tally Method. I'm just going to grab it and link it here because it's actually really simple. You stick with it, and it means that you'll never worry about how to find those regions again. Now I've got the link here. Let's see if I can put it into the chat. Yeah, I think that's a link. So this is the Fabulous Tally Method for finding regions on a Venn diagram. And the reason why I plug that in is because the notation is sometimes difficult, you know, where you have to oh gosh, no, don't do that. I actually can't write it because they want to turn it into an emoji. Alright, it's going to look weird, but there you go. There's a space after the B because apparently that's a person wearing sunglasses. But yeah, when there's a notation like probably A and B, probability of A given B, that sort of stuff can be confusing. But that method there means you don't need to think. It's actually really easy to find using the tally method. And that's it. Calculating skew, already looked at. That's skew is a formula that they give you. That's not a big deal. You can look at that. Let's have a quick look at the skew formula. So, yeah, I think we wrote that down. I think it's on here. Here it is. So what do you need? Essentially, you're going to need the mean, which could be X bar. You're going to need the median, and you're going to need the standard deviation. But once you have those three, you just put it in here. Not too bad. Yeah. I just wanted to double check the interpretation of the formula. And I did look at skew as well earlier. I looked at what things look like. Pretty sure. Yeah, it was in here. So you've got negative skew, positive, or even. Yep. Because that was by inspection as well. So if you calculate the skew, I think that's everything. And for everything else, there's MasterCard. I'll just link in the formula that you're going to get. And you just got to know what formula is best to use. So this formula is if you know X bar, and this is just if you don't know X bar, right? The other thing is that when you're doing sigma x, that's not just 1, that's going to be x1 plus x2 plus x3, etc. All the way to however many you've got. So you've got to do it one at a time and not miss anything. And that's pretty tough. That's it. Yep. I think I've got through your list. Is this live stream will be yeah, so when I end it, it goes straight into the live stream buckets and you can have a look at it again. There's there's a whole 45 minutes at the beginning where my microphone wasn't on. So that was fun. But then after 45 minutes, I go through it again. And I eventually will just delete the first 45 minutes of this live stream, but you will still have access to it. You never know what's going to come at you in the exam. These are some of the basic concepts with some examples. So you've got to hold your nerve. Sometimes that's the hardest part, you know, believing in yourself when things are new, and you just got to have this confidence, and you don't need reason for confidence, you just need to have confidence. And that's it. I have to sign off. It's nearly 3 a.m. Now you can guess exactly where I am in the world. All right, good night, and hopefully that was useful.